Yo, what's up, SUPA family? Here we are. Okay. Today we're going to start I think it's chapter 8. And we're going to deal with some bonding. So a lot of today's stuff is going to be review. There's going to be some new things. So here we go. Bonding. So when we're talking about bonding, we're always talking about using the valence electrons. So our valence electrons are the electrons in the outermost principal quantum level of each atom. And another way to say that is the outermost PEL of each atom. So those are my valence electrons. Just to review, our inner electrons are what are called core electrons. And the inner electrons in the nucleus is called the kernel of the atom. So, I don't know, let's look at magnesium. It's got 12 protons, 12 neutrons, 2 in the first, 8 in the second, and then finally 2 in our third. Right, so in magnesium, these right here would be our valence electrons. These electrons in here, okay, in PEL 1 and 2, these are called the core electrons. And then if you consider the nucleus and these core electrons together, that's all called the kernel of the atom. Now, all of our bonding is dealing with valence electrons. Okay, so we're dealing with these valence electrons. So you need to be able to figure out how many valence electrons each element has. And that's pretty simple. So if we look at our periodic table, all right, so group 1, all of this first group is going to have 1 valence electron. Group 2, these guys are all going to have 2 valence electrons. 13 will have 3, 14 will have 4, 15 will have 5, 16 will have 6, 17 will have 7, and 18 will have 8. Okay, so they're based on groups, and the number of valence electrons is what gives them those similar chemical characteristics. Now, if you have to deal with transition metals, you're going to actually have to look at those electron configurations. You're going to have to go in and figure out their electron configurations to see what the valence electrons are. So we can calculate valence electrons just by group. So you're really not calculating, right? So our group 1, our alkali metals, they always have 1 valence electron. Group 2 will have 2 valence electrons. Okay. 13 will have 3 valence electrons. 14, 4, and so on and so forth. Okay. And that's nothing new. Now, we're going to be using Lewis diagrams or dot diagrams a lot during bonding. So let's just review those a little bit. So our Lewis diagrams are going to show us our valence electrons. Right, so there's a specific way that we show these, right? So we put the symbol in the middle, and we're just going to use element X right now. And the electrons go around this in a very specific way, right? If there's one valence electron, it goes there. If there are two, the second one goes there. If there are three, third one goes there. The fourth one is going to come down here. The fifth one is going to go here. And then they eventually start to pair 6, 7, and 8. Okay. Now, why do we do that? Why do we do this weird numbering thing around the nucleus or around the element? Well, it's got to do with the shells that we're filling. Right? So if we look at this one, right, this first electron is going in the s orbital. Okay, so these are going in the s orbitals. This represents px. This represents py. And these represent pz. So if I want dot diagrams of atoms, okay, so let's say that I want the dot diagram for sodium. Well, sodium, it's in group 1, right? Its electron configuration would be 1s2, 2s2, 2p6, 3s1. Well, this right here is the valence electron. Okay. So it has one valence electron. So to write the dot diagram, we'd write an N, A, and it would have one dot top left. All right, well, what if we go next to it to beryllium? Magnesium, sorry. So now it would be neon 3s2. So these guys right here would be my valence electrons. It's in group 2, so you really don't need to do that, but we're filling that s orbital, right? So that would be Mg with 2 electrons paired, and you got to make sure that I can see those pairs. That's important. Right? Well, what if we have something like oxygen? Let's do oxygen. Well, oxygen is in group 16, so it has 6 valence electrons. 1, 2, then we start filling the p orbitals, px, py, pz, and finally go back to the px. Right, now notice, you can see how you can see these pairs of electrons and unshared pairs. That's going to be very important, right? So if I see a dot diagram of oxygen like this, 1, 2, 3, 4, 5, 6, oops, nuts. 1, 2, 3, 4, 5, 6. Right? This would be wrong. Wrong. Okay. You got to be able to see these pairs, right? Because we're going to be pairing up electrons. Finally, let's deal with a noble gas. Let's say we have neon. Well, neon has 8 valence electrons. Be 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that would be neon. All right, well, let's deal with ions. So your cations they're going to lose electrons. Right? So Na is going to go to Na plus 1. It's going to lose, if you come up here, it's going to lose this one valence electron. Okay, so normally we'd have a dot here. That electron for the metal is lost. Okay. When it's lost, we put it in brackets with a plus 1. Okay. Now, this is not saying that there are no electrons around sodium anymore. Right? So remember, this would be 1s2, 2s2, 2p6. Technically, there are 8 valence electrons around there right now. Okay, but what we're trying to show is that it lost that 3s1 electron, right? So we generally show the metals without any electrons, but just realize that there are really 8 valence electrons now around that, and that would be isoelectric with neon. That would be isoelectric with neon. Now with our anions, or our nonmetals, okay, these are going to gain electrons. So let's say we have fluorine. Fluorine wants to go to, it wants 1 electron. Oops. So fluorine has 7. 1, 2, 3, 4, 5, 6, 7. Okay, so there are 3 pairs. It's going to gain 1 electron, and you can see where it's going to go. It's going to pair up here. And I'm going to put an X, but it doesn't have to be an X. It can be a dot, but I just want to show you that. So that's where it gains the electron. And since it's an ion, it goes in brackets, and it's going to be minus 1. This, again, would be isoelectric with neon. Same electron configuration as neon. So this would be the dot diagram for a fluorine ion. Okay, so we haven't talked about this yet. Electronegativity. The technical definition for electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. The ability of an atom in a molecule to attract shared electrons to itself. Now, this is a range. It goes from 0, no, it doesn't go from 0. It goes from 0.7 up to 4.0. And what this is really telling me, it's telling me if an atom wants to gain or lose electrons. Low values, these are the metals, and these want to lose electrons. Okay, they don't want to gain them, or when they share them, they don't pull them towards them. High values, these are our nonmetals, okay, which want to gain electrons. All right. So if we look at the periodic table, and I know you can't see the whole thing, but let's start over here on the metal side. So the metals want to lose electrons. Which is the most metallic element on the periodic table? That would be francium. Okay. He does not want to gain electrons. Right? Matter of fact, he wants to get rid of electrons, and we talked about why. All right, so it's a very big atom. The electrons are the valence electron is very far away from the nucleus. All right, the attractive force between the nucleus and that electron is very small. All right, so he's not going to gain electrons. He's going to want to lose them. Now, as we move up the chart, okay, the atoms get smaller and smaller and smaller and smaller, and the attractive force gets greater and greater and greater. All right. So what happens as we move up this chart is our electronegativity values increase slowly. Now, they're still all going to be very low over here. These guys don't want to gain electrons. They want to get rid of them. Over here, on the other side, remember, fluorine is our most non-metallic element. He's going to have, excuse me, it's not a he or she. It wants to gain electrons. So fluorine has the highest electronegativity value of 4.0. Right? And it slowly decreases as we come down here. So on our periodic table, we got francium down here at 0.7, and we got fluorine up here at 4.0. So as you move across here, in general, our electronegativities increase. They want to gain electrons more and more. And then as we go top to bottom, on the metal side, they decrease. Actually, they all decrease. Now, we're going to be using these values. Okay, we're going to be using these values. And what we're going to be using, or what we're going to be doing, is what's called electronegativity difference. And what this will give us is the actual bond type. So if we take the difference of the two atoms' electronegativities, if it goes between 0 and 0.4, this would be a non-polar covalent bond. We're going to talk about that bond quite a bit. If it's between 0.41 and 1.7 to 1.9, this is going to be a polar covalent bond. And then 1.7 through 1.9, above this range, so greater than those numbers, this is going to be ionic. Now, here's the problem. This is why I'm giving you these numbers. So the line between a polar covalent bond and an ionic bond, it's not perfect, all right? So some bonds that lie in here are ionic and some are covalent. And we'll talk about that. It's not that big a deal. You don't really get into this very often, right? You don't get into this line. So in general, okay, like if you got 1.9, usually it's going to be ionic. If you have 1.7, usually it's going to be polar covalent. But it's not always. There's a fuzzy line here. But if you get to 2.0, it's for sure going to be ionic. Now, the greater the difference, the more ionic character a bond has. So if you have a big difference, okay, you have a big difference, it's going to be very ionic. If you have a smaller difference, it's going to be more covalent. Right? So I don't know. Let's see. So if we were to calculate the electronegativity difference of diatomic oxygen, okay, so oxygen is what, 3.6, I think? Minus 3.6, it really doesn't matter what it is. It gives us a difference of 0, which means the bond in here would be a non-polar covalent bond. Now, there are tables where you can look up these electronegativities. And if you remember back to your reagent reference tables, you remember back to those table S? Okay, they're listed for you. Pretty sure they're in the back of the textbook also. So here are your electronegativity values. All right, so let's say that we have a bond between carbon and hydrogen. And I want to know what type of bond that is. Well, if we look up carbon, carbon is 2.6. Hydrogen is 2.2, which is 0.4. Right? Even though they're different elements, okay, this is still going to be a non-polar covalent bond. Okay, and we'll talk more about that as we go. What if we look at, I don't know, how about salt and ACL? The bond between those. We already know that that should be ionic of a metal and a nonmetal. Well, sodium is 0.9. Chlorine is 3.2. Right, so if we subtract there, okay, well over 2. Well over 2. This is telling us that it's ionic. So you can use this electronegativity difference. Now, in most cases, really, in reality, you could look at it and say what type of bond it's going to be. Right? So if you have an HO bond, this is a nonmetal and a nonmetal. This is going to be a covalent bond. LIF. Okay. This is a metal and a nonmetal. This is going to be ionic. All right, but if you want to know for sure, you could do these electronegativity differences. All right. So let's get into chemical bonds and energy. So if you look around your room, or you look around my room right now, most substances are in compound form. They're not in elemental form. Okay. What does that tell us? So most substances are in compound form. Well, what that's really telling us then is that compounds are very stable. And remember, as soon as we start saying that word stable, what we're really saying is they probably have low potential energy. Right? That's really what we're saying. Because remember, nature likes having the lowest possible potential energy. So what is a chemical bond then? Well, a chemical bond forms when the atoms are arranged such that they have a lower energy than the sum of the energies of separate atoms. So what I want to do is I want to show you this. All right, so what we're going to do is we're going to look at the formation of hydrogen. I should say a hydrogen molecule. So we're talking about potential energy here when we're talking about bond formation. So there are two unfavorable PE terms in a bond. And that pen is dying. One of the unfavorable terms is the proton-proton repulsion in the nucleus, or not in the nucleus, between the two atoms. So when two atoms are coming together, like two hydrogen atoms, the nuclei themselves repel each other. The second thing is an electron-electron repulsion between atoms. The electrons of one atom are going to repel the electrons of a different. So there are two unfavorable PE terms. Let's use this. There is one favorable PE term. And that is the attraction between the protons of one atom and the electrons of a different. So that proton-electron attraction. So when we start forming bonds, okay, and let's talk about this hydrogen bond. The two hydrogen atoms will position themselves so that the system will have the lowest possible potential energy. So let's write this. So our system will minimize the sum of the positive and negative repulsive energies So they're going to settle in a difference that minimizes this positive and negative repulsive energies between the atoms. And this is what determines the bond length. This distance determines bond length. Right, now, this is a bunch of words. So let's see if I can kind of show what happens. I want to show you kind of what happens. So let's say we have two hydrogen atoms. So we got one proton, one electron. So when they're far apart, there are no attractive forces. Or repulsive forces. So now what we're going to do is we're going to bring these atoms closer together. And eventually, when they start to get closer together, they start to interact. They start to interact with each other. Right? And you start to get these electrons repulsing each other, these protons repulsing each other, and you actually also get an attraction between this electron here and the protons over here, and the electron here and then the protons over here. Right? And eventually we form a bond, and those valence electrons, and this is simplified, okay, those electrons start to be shared. Okay. This distance for hydrogen is 0.074 nanometers. And it's the optimum bond length for hydrogen only. And at this distance, the attractive forces balance the repulsive forces. Now we can actually graph this. This is going to be PE. This is 0. Usually this is in kilojoules per mole. And this is going to be internuclear distance down here. And when we're forming a bond, when we look at this, okay, the curve generally looks something like this. Now, let me explain what we're seeing. So out here, these are at great distances. Okay, and here we're having smaller distances. So now, this right in this area right here, this is where the hydrogen atoms are far apart. So there is no interaction between them. Right? So as we go this way, the distance between the hydrogen atoms is getting smaller. Now, eventually we get to a point where they start to interact with each other. And as they start to interact with each other, the potential energy goes down. And eventually it bottoms out right here. And it turns out that this is 0.074 nanometers. That's where we have this hydrogen-hydrogen bond. Now, what happens to potential energy if we push these two closer together? Well, if we push them closer together, okay, if we get them closer together, well, the repulsive forces are increasing, right? So my potential energy is going to skyrocket. So this optimum bond length is where my potential energy is the lowest. Okay? So if we force those atoms together, the repulsive forces increases because those proton-proton interactions, right, those are pretty strong repelling forces, right? So it doesn't want to be closer for hydrogen than 0.74 nanometers. Right? Hopefully this makes you understand a little bit about what's happening with these attractive forces. All right, so let's talk about ionic bonds today. So an ionic bond is a force of attraction between atoms that is a result of the transfer, having trouble here, of electrons from one atom to another. Force of attraction between atoms that is a result of the transfer of electrons from one atom to another. This electron transfer creates ions creates oppositely, sorry, having trouble here all of a sudden, charged ions. The attractive force is called an electrostatic attractive force. And if you remember, really what we're just saying is that a positive is attracted to a negative. So that's what our ionic bond is. Now, let's talk about the octet rule. atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. This fills the s and p orbitals, which is a noble gas configuration. And this has the lowest potential energy. So they want those stable s and p orbitals filled. All right, so that's why they want 8 valence electrons. Now there are a couple that only want 2. Right, so they want this noble gas configuration. Right? But hydrogen doesn't want 8 electrons. It wants to be like helium. Well, helium only has an s orbital, so it is going to only want 2 valence electrons. So hydrogen is going to gain 1 electron to become like helium, right? So he only wants 2 valence electrons. Lithium. Okay, lithium has 3 valence electrons, and it wants a noble gas configuration. It's going to lose this 1 electron. Okay, so it would be 1s2, 2s1. Okay, it's going to lose that 1 electron and become 1s2, like helium. So lithium is another one that only wants 2. Beryllium is another one that only wants 2. Sometimes boron only wants 2. All right, so there are a few atoms that only want 2 valence electrons. All the rest want 8. They want the full s and p orbitals. And the reason these guys only want 2 is because in that first PEL, there is only an s orbital to hold 2 electrons. Now, when these ionic bonds form, what we said is they have lower potential energy. All right, so let's look at NaCl. Na has 1 valence electron. Cl has 7. Now, these are going to interact, okay? Sodium wants to get rid of this 1 electron to get its electron configuration. Chlorine wants to gain 1. So this is going to be an ionic bond. The sodium is going to donate that electron right here. It's going to pair up. So sodium gets a +1 charge. And remember, we don't fill in the electrons around the sodium. The chlorine is going to gain that electron. Right here, it's going to pair up. It's going to get a -1 charge. Now, this is held together by an electrostatic attraction. The positive is attracted to the negative. All right, now, if we talk about some things that we talked about in chapter 7. So chlorine has a much higher affinity for electrons. Sodium has a much lower ionization energy. Sodium's electronegativity value is much lower than chlorine. Okay. So all of these reasons are driving this transfer of electrons. Right? So because of all these different things, the potential energy decreases as the bond forms. The molecule is more stable than the atoms. Oops. Come on. Apart. So together, these atoms are much more stable than if they were apart. Right? So apart, it doesn't want this one electron. It wants to get rid of it. It's not stable. It'll be more stable with an 8 valence electrons. Chlorine is the same thing. It wants that electron. It's going to gain that electron, okay, to become more stable. So together, they are much more stable than they are apart. Let's look at let's look at calcium bromide, just in case you're asked to. Right, again, this is an ionic. It's a metal and a nonmetal. Right, so calcium, it has 2 valence electrons. There are 2 bromine atoms. Each one of these has 7. This is where this formula is coming from. Calcium wants to lose 2 electrons to get that noble gas configuration. A bromine can only take 1 of them. So I need 2 bromine atoms to take one valence electron from the calcium, which is what's giving us this 1:2 ratio. So one of these electrons is going to come down and pair here. One is going to be donated there. Calcium is losing 2 electrons, so it becomes +2. Br is gaining 1 electron and becoming -1. Okay, now what holds this whole thing together? Well, we have these electrostatic attractions again. Okay. Now, our ionics. Remember, these are mostly our salts. So in solid form, a 3-dimensional lattice forms and is held together by strong electrostatic forces. And I got this model out again, and it's going to be hard to see here because I can't zoom out anymore. All right, so here's my model. Actually, let me see if I can do this. Can I do this? Yeah, I guess I can. So we can do this. And so this is sodium chloride. Right, this is that 3-dimensional lattice that we've looked at before. Right, so this is my cation. There's my sodium. Right, this is my chlorine. Right, and this is an electrostatic attraction between them. But there's also an electrostatic attraction here, and here, and here. These are all electrostatic attractions. Now, look at all the bonds that are holding this guy in place right here. There's 1, 2, 3, 4, 5 electrostatic attractive forces holding that in place. Right? Same thing down here. Same thing down here. Because of all these strong electrostatic attractive forces, this solid, ionic solid, is actually really, really hard, and it gives us some different properties that we should talk about. Okay. Let me get focused here. So these ionic salts, they give us that three-dimensional lattice. Let's see if I can kind of draw it. All right, so if these are our positive and negative atoms, this would be an electrostatic force here, an electrostatic force here. So I'm trying to show you this lattice. So there's all these bonds in here, all these ionic bonds holding this thing together. All right. So when this forms, when this lattice forms, this is an exothermic process. Energy is given off as these bonds form. Right? So as the Na plus Cl comes together to form our NaCl solid, right? It's exothermic. It's given off a lot of energy because this becomes more stable as the atoms come together. Now, ionic solids have some very special properties. Because of all these bonds, they are really hard. They have high melting points. High boiling points. They're brittle. If I hit them with a hammer, they're going to shatter, right? Because they don't want to reform. They want that nice, strict geometric lattice, right? So this is our ionic salts, or our solids. So let's look a little bit closer at the energy associated with these bonds. So Na plus Cl turns into Na plus, Cl minus. There's my dot diagram. And we can actually look up the heat of formation. And it's negative 410.9 kilojoules per mole. So it's a 410. All right, so it's telling us that it's very exothermic. Now, we know that that guy is losing electrons, and the chlorine is going to gain that electron. So when a substance loses electrons, it is always endothermic. It's ionizing. Okay, so we have to add energy, has to be absorbed for the electron to leave. And it turns out the first ionization energy for sodium is a positive 496 kilojoules per mole. electron gain is exothermic. And actually, the gain of an electron for chlorine turns out to be negative 349 kilojoules per mole. So if we add those two numbers, we should get this number, right? Well, if we take 496 plus a negative 349 kilojoules per mole, it gives us positive 147 kilojoules per mole. This is saying that this is endothermic. It's not. It's very exothermic. So there must be something else that's going on here. There's got to be something else that's going on here. And that's called lattice energy. So lattice energy is the energy required to completely separate 1 mole of an ionic solid into gaseous ions. Okay, that's how we define lattice energy. So for example, what I'm really saying here, if we take NaCl solid and we add energy to ionize it into a gas, the delta H of this is positive 788 kilojoules per mole. To separate these atoms from that bond, we would have to add 788 kilojoules per mole. Now, what if we reverse this? What does that do to the delta H? Changes the sign, keeps the magnitude. Going that way is very, very, very exothermic. So it's telling us that as this solid is forming into its lattice, okay, it's giving us a ton of energy. So it's not just electrons being lost and gained over here. Okay, it's as that bond forms into this solid lattice, it's also giving off energy because that solid lattice is very, very, very stable. Now, the magnitude of the lattice energy of an ionic solid depends on the charge of the ions, their size, and the arrangement in the solid. So the energy, and this is the energy of the lattice, is equal to a constant times Q1 times Q2 all over distance squared. Okay, so this energy, this lattice energy, right, really has to do, this constant doesn't change it. Q1 and Q2, those are this is the charge of the ions. The distance between when this forms, when these ionic compounds form, the distance does not change much. It does a little bit, but not very much. So our big change is the charge of the ions often. So the magnitude of the ionic bond, or the strength of the ionic bond, depends mostly on the charges of the ions. So we can compare lattice energies between different compounds. So let's just try this. Determine relative lattice energies between NaF, CSI, and CaO. Okay, which is going to have the strongest lattice energies and which one's going to have the weakest? Well, if we go back to that formula, E equals K Q1 Q2 all over distance squared. Okay. For all three of these, this distance is relatively close. Okay. And we're going to talk more about that in a minute. All right. So the distance between the atoms themselves it's not constant, but it's pretty close. So it doesn't change much. So what's going to really tell us what's going to happen with our lattice energy is our charge. So if we go look at this, sodium is +1, fluorine is -1. This is +1, -1. This is +2, and this is -2. So here's my Q in Q1, Q2 here. This one's going to have much more lattice energy, right, than just the +1, -1, right? So we have a bigger opposite charge here is what I'm really saying. A +2 charge is much more attracted to a -2 charge than a +1 and a -1. So this guy automatically, because of this charge difference, is going to have the highest lattice energy. Okay, because of the charge difference. Now, we also need to be able to figure out this, and this is where distance does come into it. And when we're looking at distance, we really need to look at the size of each atom. When we're talking about this, the larger the atom, the bigger the distance between atoms. So we want to compare these two. Okay, so we're comparing NaF and CSI. because they're both +1. So we can't figure it out by the charge, which one has more lattice energy. Right? So if we look at Na and compare it to Cs, this one is much bigger. It's a bigger atom. Okay. The electrons are further out. It's got more PELs by quite a bit. If we look at fluorine and iodine, again, this is a much bigger atom. Much bigger. So the distance between these two is much greater. It's not much greater, but it's bigger. They're further apart. So that means the distance between NAF is smaller, which gives us a stronger force of attraction, which gives us a higher lattice energy. It gives us a higher lattice energy. So if we were going to put these in order, okay, from greatest to smallest, CaO would have the greatest lattice energy because of that charge difference. NAF would be next because the distance between the atoms, the strength of the forces is closer, so it's a stronger force of attraction. And then CSI would have the least amount of lattice energy. Okay, so I would expect you to be able to do something like that. Okay, so that's where we're going to stop for today. I don't want to get into covalence today, so let's stop with that today so you can work through some things. And we will pick up with covalence next class.